All right, let's get started with the first lecture and initiate this with two presentations by the students about some, well, very old, interestingly, techniques that started out the field. And we'll see more about them as they present. Go ahead.
Hi. Okay, I'll start. So, hi everyone. My name is Amay Gada, and I am a third year computer engineering student here at DJ Sangvi College of Engineering. So today I'm going to present a paper on the Viola-Jones algorithm, which is much more famously known as the Haar cascade. And it is pretty interesting to get into this because it is a very efficient algorithm, which also is still giving like a hard time to existing algorithms, which are made using deep learning. So to begin with, let's discuss the objective of this algorithm. In an image, we have to look for squares and rectangles that might enclose a face. So the question is, how do we go about doing something like that? One of the initial ideas is to directly use pixel values. All images consist of nothing but pixels, and we can leverage that to make a classifier. However, Viola and Jones had slightly different plans. Just before I move on, I would like to clarify that the image on the right is for a colored image. In Viola Jones algorithm, we have only one channel, and hence the image is black and white. And yeah, so Viola and Jones believed that each face could be detected by looking for something they called Haar-like features. Haar-like features are certain patterns whose combinations, when found in an image, determine if it is a face or not. And some of the Haar-like features are shown in the image on this slide. So, and now it would be a very valid question to ask, like, why are these features valid? So, like, if you would imagine yourself in a picture, sometimes the nose, if you visualize your nose, sometimes the bridge of your nose is whiter than the edges, and this feature E tries to like depict that kind of pixel difference that is existing around your nose or on your nose. And moreover, um, these features can be extended to many different sizes, right? Because you cannot just have, if someone would have a larger nose, someone would have a smaller nose, and sometimes these a 2 x 2 pixel might not do justice to the entire or to one of the features that we really want to encapsulate. So what we do is that these features can be extended to many different sizes to incorporate all tiny and large details that that face might consist of. And what I mean by this is that the feature D is just looking at a 2 x 2 matrix now. It can now further be extended to look for a diagonal spot in a 4 x 4 or a 5 x 5 pixel matrix. So now, considering all the features in all their sizes, we end up having around 180,000 features. And moreover, these 180,000 features are looked for in a 24 × 24 sub window in the image. And again, let me go back to the previous slide to explain what I mean by 24 × 24 sub window. Now let's consider that we are looking for a face in this image. So what I do is I start from the top left. I have a 24 × 24 sub window. I look for a face over here. Then I move slightly towards the right. Then I look for a face over here. Then I move slightly towards the right and repeat the same thing until I find faces or until I reach the end of the image. Finally, before I moving on, I would like to read this out so that you know why they use features instead of pixels. And this is directly taken from the paper. So they say that our object detection procedure classifies images based on the value of simple features. There are many motivations for using features rather than the pixels directly. The most common reason is that features can act to encode ad hoc domain knowledge. Ad hoc means necessary. I had trouble with that earlier. Anyway, that is difficult to learn using a finite quantity of training. Moreover, the feature-based system operates much faster than a pixel-based system. Okay, so now 180,000 features is a lot. Hence, the authors of this paper came up with a very intelligent trick to calculate the sum of pixels in a given pixel matrix. So as we've seen earlier, our objective is to find the difference in the sums of pixel matrices. So what I'm talking about here is that how do we know that this feature exists? We see the white pixels have value closer to 1 and the black pixels have values closer to 0. So we sum up all the white pixels and we sum up all the black pixels and then we subtract them and we normalize them such that the values come between 1, 0 and 1. And if the value is greater than 0.5, we say that, okay, this feature exists in this particular area. and if it is less than 0.5, we say that the feature does not exist. So now it is clear that the basic thing is to find the sum of pixels in a sum of sum of pixels in a pixel matrix. So these people found a way to do it in constant time, and this was done by creating something called as an integral image. Now let's see let's see how to build an integral image. So consider this is your original image, and I've just used all ones here for simplicity. And if you were to make an integral image out of this, so an image, so the value in the integral image at this position would be the sum of all the pixel values towards the left and above it. So this is 1 plus 1 and 2. And the value of the pixel in the integral matrix in the integral image at this position would be 1 plus 1 plus 1 plus 1. And similarly at this position it would be all these, the sum of all these pixels. So now how our integral image is actually helpful. Now that we've built the integral image, we must address how it is useful in aiding our objective, which is computational efficiency while finding the sum of a pixel matrix. So now consider that you want to find the sum of the pixel matrix highlighted in green. Following a naive approach, we do a 1 plus 1 plus 1 plus 1 and get 4. But now, if we were to use integral image to do the same thing, we would need mere 4 references to the integral image. And these 4 references are highlighted in red right over here. What you do is 9 plus 1, 10, and then do 3 plus 3, 6, and do 10 minus 6, which is 4. And it might seem not a very efficient computation for now, but you can very well imagine that this matrix could be something like 17 cross 10, and then you would have 170 computations to do, and instead you can just do it in 4. And this below are just images of formal description of how the paper in the paper of how the authors presented the. So okay, wait. So this is the integral image, and this is the recurrence relationship which is used to build the integral image. So now integral images help a lot with reducing the time complexity of finding features. But having to look for 180,000 features in each sub-window, even with the help of integral images, can be detrimental to the real-time needs of this algorithm. So this is where AdaBoost comes in. It focuses on the fact that not all features are relevant in determining the existence of a face. Therefore, only the important features can be kept and rest can be discarded. So for example, the feature E that we saw earlier, right over here, would be relevant where the nose is, and it won't be relevant anywhere else. Anyways, the classification of important features is done by this algorithm called as AdaBoost. And along with this, AdaBoost is also used to train the classifier. Now, AdaBoost trains weak classifiers, and a linear combination of these weak classifiers will give a final strong classifier. A weak classifier can be seen as a single node decision tree. And here a weak classifier is only restricted to one Haar-like feature. So I made this flowchart to have a very beginner-friendly understanding of how the AdaBoost algorithm works. So I just realized I put the arrows all wrong. If you could ignore that, I'm sorry. So the input goes, and we assign equal weights to all the inputs. Now these weights are different from neural network weights. Okay, so we assign equal weights. We normalize those weights, and after that, we train the classifier for each feature. We update the weights, and then we choose random image from training data again, and we normalize the weight again. We repeat this process, and every time we're doing this, we keep on choosing the best classifier that comes around. So this is our weak classifier, and keep on adding to our list of weak classifiers. And hence we'll use the linear combination of all these weak classifiers to make a strong classifier towards the end. And the next slide shows the contents of the previous slide written formally. Right. So this is the weak classifier, and this is the entire AdaBoost algorithm which I summarized in this flowchart. Now, finally, the authors give this algorithm a final touch with the attention cascades. Now, attention cascades are nothing but increasingly complex set of classifiers that the input image will go through one by one. So now, if one of the classifiers classifies the image as not having a face, classifies that sub-window as not having a face, we immediately reject it. So we are no longer doing further processing or further classifications on that window. And now there is a valid question that would come here, which is that how can we be so sure that the model will not give false positives? So the authors claim that we can actually modify this theta value, which is nothing but a threshold, to in such a way that there'll be no false positives. So this is where the Haar cascade algorithm ends, and this is final the final model that actually helps the algorithm to detect your face in the entire image. Thank you.
Thanks for the talk, man. Does anyone have questions about? Okay. Whoever did that, avoid doing that. Do you want to continue recording? Okay, there are questions. Cool. Why do we normalize the weights? I think you mentioned normalization in the flowchart you were showing us, or are you talking about something else? Mohammad Sharik Nawaz. In ADA Boost. So the flowchart, do you know why you normalize the weights?
I think so. I think that we actually use the weights such a way that we use the weights to actually help the classifier do more work on negatively classified images. So what normalizing helps us do is that everything is from a single distribution. I don't know how to explain it, but I think you could do a better job at explaining, Swapnil.
I think normalization here is not special other than normalization anywhere else, where you want to reweight it and then normalize again because that reweighting might have thrown your original normalization off. Like if I have a dog image and suddenly I come across a cat image, that throws some weights off, and you want to go back and normalize it such that you are equally accounting for all the training data. I don't know if that makes sense here.
I mean, in the paper they say that they're normalizing so that they come from a single distribution, so that WT is a
Hmm.
probability distribution.
Hmm.
This is what they say is why they normalize the weights.
Maybe I wasn't mathematically precise, but that was my intention. That was what I was trying to get at.
Okay, okay.
So when I said account for all images equally, I meant like it's a probability of each image affecting the weights. Um, but yeah, this is the difference between saying things and like being mathematically formal about them. So that's great. Cool. That was a little over time, but it's the first presentation I've ever had, so I wasn't very finicky about that. We can now move on. Thank you so much for that. That was well presented. We can move
Thank you.
on to Joseph and Jagrut. Take it away.
Hi, everybody. I'll be ready in 1 second. There we go. Alrighty. So, good morning, everybody. My name is Joe, and my project partner is Jagruth. And today we're going to be presenting on semi-supervised machine learning, but we're going to go over our project first for a minute or two just to provide some additional context. So, on the surface, our problem looks like it is a supervised machine learning problem where we want to take a function that takes in a piece of text from a tweet and then returns 0 for this is not an injury statement or 1 for this is an injury statement. So in the top tweet over there is not an example of an injury statement because the context of the statement is actually about an engagement that's gone wrong at a baseball game. So that should be a 0, but the bottom one should be a 1 because we're talking specifically about COVID, as in players on the Yankees team got COVID, and so they had to stop practice. So that should come out as a 1. But there is a bit of a problem with this, and that has to do with the sheer number of tweets that are available. So these have to be labeled by hand, and so this is a bit of a problem because I can really only realistically do maybe 300 or 400 a day, but I'm easily getting on the order of thousands at a time. And actually at this point in time, I have somewhere around 100,000. And so it's getting a little bit messy. And it's been growing exponentially as well. So I imagine by the end of the semester, it looks a little bit more like this by the end. So I'm going to probably at the end of the semester, I'm probably going to have like maybe 4,000 or 5,000 labeled, but then I'm going to have somewhere close to 1 million unlabeled. But thankfully, there are methods in order to take advantage of the unlabeled data. Usually what goes on is that they take place in the form of like clustering algorithms that take place during the supervised learning, and which is the more modern version of semi-supervised machine learning. I'd also like to point out that this is also called multi-view machine learning as well as semi-supervised machine learning. So this presentation is not about web scraping, but I want to just go over very quickly how the web scraping pipeline works. So I'm getting accounts from 3 websites that I wanted to take a look at because they're verifying whether or not this person's a journalist or a baseball player or something else. So those are the kind of people I want to look at their tweets at. And then I'm using the Python library Twinks as the tweet scraper. That's using that's doing all the scraping. It's only like 10 lines of Python code and it drops the CSV file for me. Once I do that, I have Python label some of them because some of the tweets that I'm getting off the website, they're injury statements already. I can just label them immediately through Python, and then some I'm doing by hand, and then that gets converted into the CSV file. So, and at this point in time, I have 1,500 sources I'm tracking, and then 177,000 tweets. If you want to learn a little bit more about web scraping, I actually have been doing web scraping for a few years. And so at that hyperlink is actually a 30-minute presentation that I do on the subject. But at this point, I'm going to swap over to my project partner, Drew, and he'll talk a little bit more about the machine learning algorithms themselves.
Hi, this is Jagrut Lalwani here, third year electronics student from VGTI. So as Joseph have mentioned that we are going to use semi-supervised learning. Now, since we know that unlabeled data is cheap and easy to get, whereas labeled data is very hard to get and is usually expensive, human annotation, as mentioned, is very time consuming and labeling may require expert view. And at this moment, a question may arise that why not, employ supervised learning at the limited amount of labeled data which we have. But we cannot do that as we may run into a problem. Next slide, please. So on the left side, we are not having unlabeled data, and we try to create a decision boundary between the 2 labeled instances. And here, as we can see, we can have a number of decision boundaries without the unlabeled data, but that is not the case when we have unlabeled data. When we are using unlabeled data, here we are having a more accurate decision boundary in the presence of unlabeled instances, and this helps in increasing our accuracy of our model. Next slide, please. So what we're going to use, the method which we're going to use is also known as co-training. Now, this is a classifier which uses inductive semi-supervised learning. Now, semi-supervised learning are of 2 types, transductive learning and inductive learning. Transductive learning does not generalize the unseen data. It produces labels only for the data at the training time. It assumes the labels and trains the classifier on assumed labels. Now, here, inductive learning, what it does is it generalizes the unseen data. It not only produces the labels, but also helps us come up with the final classifier and uses manifold assumption. Now, the method which we'll be using here is also known as bootstrapping, where we start with a few basic seed rules, which are typically high precision row recall. We build an initial classifier, use this classifier to label the unlabeled data, extract new rules from the pseudo labeled data, and build a classifier for the next iteration. We exit if the unlabeled data is unchanged, and otherwise we reuse the classifier for unlabeled data and continue. So generally, when the co-training model was first introduced, they assumed 2 classifiers. One was the local classifier and another was topical classifier. But we can use multiple models based on each attribute or kind of data, which has its own perspective or view of the data. Now, what we make 2 major assumptions here. One is that each view will be sufficient to classify all of the data, and each view is conditionally independent of the other views. That is, for example, if one One view is classifying objects based on their color. Other view is classifying based on their size. Now, these two cannot be in any way interdependent. Hence, they're also known as conditionally independent. Now we select those unlabeled data which were most confidently predicted by these models and add those to the training data. That is, we add instances labeled by classifier C1. Here we are using two classifiers, just for an example. So we add instances labeled by the classifier C1 to the training data of classifier C2 and vice versa. We repeat the process until the data is exhausted. And as mentioned, we generally use two complementary classifiers which are used to bootstrap the performance of each other iteratively. Next slide, please. So I'm just going to pause. This is just a pictorial representation of the co-training approach. Next slide, please. Yeah. So possible issues which may run into here are namely two. We could come up with two possible issues. One is the sample selection step generally ignores the distributional bias which is present between the unlabeled and labeled data sets, resulting in a significant difference in the sample distribution. That is, after iterative co-training, the sampling bias may shift towards the unlabeled data set, which results in a very poor performance of the trained model at the testing time. Other is that the existing sample selection and the training can be myopic. That is, only those unlabeled examples which align well to the current model will be picked up during the iteration, and the model might totally fail to generalize the concept of the complete sample space. Next slide, please. Now, a possible solution here is reinforcement learning based framework for co-training, where after each iteration, we'll check what the results are. We reward the good results and penalize the wrong results. And basically that is what reinforcement learning. So this is not totally semi-supervised learning, but a mixture of semi-supervised and reinforcement learning. Next slide.
I'll be presenting this last slide. So up to right now, our presentation has been very co-training heavy. And I'd like to point out that that is not necessarily the only semi-supervised machine learning model. Co-training is actually very, very old. One of the first papers on it that we're going to reference in a second is actually from 20 years ago, which is ancient history as far as this topic goes. So I'm going to give two more just examples really quick before we finish. First is called canonical correlation analysis. This is also very old, I should point out. The idea is that we're going to have two completely different data sets, X and Y, as in the columns of them are not going to be really related in any way. And then we're going to try and find parameters W that maximize the correlation between the two data sets. This is not super directly useful for our projects because X and Y are not different data sets, but they're actually the same data set. One just happens to be labeled, one happens to be unlabeled, just due to limitations of doing it by hand. But this is generally used quite a bit. It's usually used for statistical analysis when people want to study the relationship of the variables between these two data sets. And so it is very useful for that purpose. The other algorithm that I have on this page that is much more modern is the Laplacian SVM. What makes it modern is most modern semi-supervised machine learning algorithms tend to assume something about the shape of your data, and then use that shape in order to classify things. So in the image over here, we have the example just two labelings on top, and then we have a bunch of unlabeled data, which is marked as gray, and this gray data has this distinct separation between the two classes. And so we assume that the classes kind of exist on different manifolds, different abstract shapes that are distant from each other. And because they're distant from each other, we can draw a line between them. And so yeah, that kind of generally sums up what modern algorithms of this kind of look like. And then lastly, we have our references here on the end of the slide. So thank you very much for listening, and please let us know if you have any questions.
Awesome. I will ask that you put the questions in chat since we're at a half an hour inside the lecture instead of the 10 minutes. Well, I had very ambitiously planned. But we always have to start the chat. So I will start the lecture now. And thank you both the groups for the presentations. These were really well built, well developed. You sent me your materials on time, and we had a session of review beforehand. So I'm thankful for that. And so with that, I can start sharing my screen. And hopefully my cursor won't disappear anymore. Are my slides visible, or do you see presenter notes?
I see the slide.
Cool. So today we're going to talk about convolutional neural networks.
Sorry, I want to clarify. I see 3 slides, or I see 2 slides, and I see presenters notes.
I don't have any presenters notes, but yeah, thanks. Okay, this should be better. Slide should have disappeared. Go back and share desktop one. See the slides. Okay, sounds good. Cool. So today, let's talk about convolutional neural networks. But before I do that, I want to start by using this motivating example of for those of you who have ever taken an art class or even generally looked at someone sketching, can you tell me how you draw a face? And at this point, you can either raise your hands or unmute and talk about it, because I don't want you to waste your time typing. The question again is, how do you draw a face? Okay, so Ashish says like an oval. Okay, I drew the oval. Now what?
We then try to place 2 eyes in
Okay,
between.
so we do an oval, and then we do 2 eyes. Now what?
And a smile.
A smile. Okay. Okay, so I draw some hair. I draw some ears. Are you going to tell me this is a face?
Kind of.
So to some of us, this might be arguably a face. But I think most of us, I'm going to go ahead and say, would disagree. Most of us have this, yes, this might be a pig face because it looks, because pigs have hair or a beard. I don't know. Anyway, the you do follow the point I'm trying to make. So the point is, there is a certain positioning. The nose is between the 2 eyes, the mouth is below the nose, between the 2 eyes, and the hair is on top of the head. So you've used some concept here that essentially is the foundation for what convolutional neural networks are trying to do. CNNs are just a specific kind of neural network that were developed to work on images with this motivation of understanding what is going on in this image. So just as we divided a face into these different parts, maybe I should use a different color. Just as we divided a face into these different parts where we said has 2 eyes, 2 ears, 1 smile, but with a certain positionality, we want the CNN to understand that if there are 2 eyes, a nose, and a smile arranged this way, it should be a face. Like you should recognize it as a face. And to be more formal, the first thing we discussed was, okay, I should have started with this, but if I give you a piece of paper, like it didn't matter if I drew the face here. I don't know, I'm deliberately drawing badly, but generally draw better than I am drawing this here. If I drew this face on the left of the page, or if I drew a face on the right of the page, it shouldn't matter. It's still a face. If I draw two eyebrows around it, it's still a face. If I miss out drawing on one ear, uh, not ideal, but it's essentially still a face if most of the parts and the location are present in the right way. And so the point I'm trying to get at is one, location does not matter. It doesn't matter where on this page I drew this face, it was still a face. Two, relative location does matter. Relative location of what? Well, relative location of the parts. And so with that, we come to this idea that, wait, we drew a face by a composition of its parts, right? So, and for final point, the composition of parts just implies the face, eyes, nose, ears, whatever. And the point of the last point I wanted to make is it doesn't matter if I draw up a hand here. It doesn't matter if I draw a chainsaw here. This is still a face. And so beyond this window or whatever you want to call it of this face, it doesn't matter if you draw a ball, football to be precise, whether you draw like a dog, um, or whatever, like there is a certain, again, I'm going to call it a window beyond which you don't care about what is in the picture or on the page. A face is a face, just because it has these objects placed close together within a certain space, and that's what you want your classifier to detect now. So again, I'm going to put this under the relative location idea, that beyond a certain window, so it doesn't matter, all you need is certain parts to be located within this area to be considered a face. And we'll get back to this because convolutional neural networks have these properties that you are told, but I found it more useful to motivate it in the sense of like, this is, if this is how we draw faces, then this is what we want, or this is how faces look like, and this is what we want the classifier to detect. So let me get back to the slides. And we can dive into convolutions. Cool. So typically, and I think we've spoken about this before, but images are represented as numbers. So one image can be represented by a matrix of numbers with values indicating pixels. Correct me if we haven't spoken about this, and I can. There you go. Correct me if I haven't spoken about this, and we can talk about that. But for now, I'm going to assume I have. And so an RGB image, which is a red, green, blue image, has 36 million elements if it's taken with this 12 megapixel camera. Well, why is that? 12 megapixel indicates 12 million pixels and three channels, which is one channel for red, one channel for green, one channel for blue, indicates that it has three different sets of these 12 million elements, which makes it 36 million. And what Smola says is if you have each hidden unit, if you have a single hidden layer with 100 hidden units, then each unit will have to deal with 3.6 billion parameters. Or sorry, the multi-layer perceptron will have 3.6 billion parameters, and that's a really, really big network to learn because you might not have enough images. Typically, you would require one or two images to tune each parameter, and so you need about, I don't know, 3.6 billion to 7.2 billion images to actually train this neural network. But that's not true. Like that's not what we see in practice. So what's going on here? Or To be fair, that's not even like we don't have those many images of cats and dogs to train a classifier. So what's going on here is again driving home the point that these 3.6 billion parameters typically in floating point 32 indicate 14 gigabytes of memory requirement, which is pretty unreasonable to have, which is pretty reasonable to have these days. But when it was starting out, it was still pretty expensive to get the GPU with the 16 GB RAMs. Um, and this is just for a simple classifier. We were not even going more than one hidden layer. So you can imagine that it gets worse. Um, so what is the solution? Well, we already spoke about this, and Smola gives a nice example. He says, well, look at this. There is this game or this find this in the picture game that kids play called Where's Waldo. And essentially, the idea is Waldo is hidden in a complex image on a particular page, and you have to find Waldo. In this case, in the image, it's fairly reasonable to say everyone is dressed as Waldo. So Waldo is basically everywhere. And so the way you detect Waldo is you might say both of these people are fairly good samples to consider as Waldo. And so we found Waldo. But like, what did we do when we found this? He's trying to go for the same idea of we don't care where Waldo is present as long as the relative features of Waldo are present. So this, in addition to a face, we want black spectacles on the face and we want a red and white hat that Waldo has, as you might see on this in this sample image out here, right? And so locality matters and it is translation invariant. So wherever in the image it is present, we don't care. All we do care is about relative location and locality. And so he jumps into this idea that if your image or your hidden representation at a hidden unit, it looks like Hij, which is, and again, you don't have to jump into this indexing stuff right now, but the reason I'll explain why we're getting into it. Um, what we're saying is if you consider if you originally have just a weight matrix that is 2D and you want to convert this weight matrix into a 4D weight matrix, you can actually do that as long as the number of units is the same. So something like 2 cross well, sorry, let's go with an easier example. 4 cross 4 can be converted into 2 cross 2 cross 2 cross 2. Why is this? Well, because the number of elements is the same. You're just reshaping the matrix. But why do we care about this reshaping? Well, you can think about this, and this is the point where I will say, correct me if I'm giving you the wrong idea. But what you're saying is this K and L. So I and J. Okay, let's start at the bottom. I and J are indicating of where you want to start. I and J are indicative of where you want to start this looking for Waldo. So this is your point IJ. And A and B are indicating the offset for the box that you will draw bounding Waldo. And this is the idea of you place a weight matrix on top of your image to capture that part of the image specifically. That's why I'm talking about weights and images together. And image is again a matrix of numbers. So you place a small matrix on top of a large matrix in order to detect that particular part containing some object of interest. And we already spoke about Haar cascades in the presentation. So the general idea is you want to detect certain features that are representative of the object you're trying to look for. So a face would have 2 eyes, 2 ears, 1 nose, 1 mouth placed in a certain relative positioning that makes it a face. So that's what you want to detect by placing this weight on the image matrix. So yeah, so what the idea here is that you can reindex this as position and then offset. But we already discussed that really position doesn't matter in the image. You could place it anywhere. And so this reduces to the idea of a convolution, where you say that now instead of like picking a place on an image and placing my weight matrix on it, I'm just going to slide my weight matrix and place it everywhere on the image. And this placement everywhere leads us into this idea of sliding the weight matrix over the image, which is in a sense a convolution. And you should note that there is this overlapping idea of convolutions and cross correlations, and convolutions are implemented in PyTorch, even though it's called conv2D. It's actually a cross correlation operator, which is super interesting, because people don't point that out as clearly. In fact, my friend who was in the second or third year of his PhD program just told me about this yesterday, and he was like, "Oh, dude, this is how it works." And I was like, "Oh, wow, okay." And then I saw Smola's lecture, and I was like, "Well, he's teaching the same thing, except to undergrads," and that's super cool. But what you should note is if you try to do convolution mathematically, and if you use PyTorch, you're going to get different answers because PyTorch is using cross correlation. Cross correlation is saying I have two functions. One is like this displaced version of another, and I want to compare how much similarity there is between these two functions if I adjust this displacement. So again, hand wavy explanation, but hopefully that sort of gets you to see that, okay, I'm seeing the relationship between these two displaced functions, and seeing if they actually map onto each other, or if they roughly map onto each other, or if they don't map onto each other. So cross correlation measures that property. And yeah, and so by multiplying this weight matrix, I should multiplying this weight matrix with this image, you're basically calculating if there are certain patterns in this area that match certain features that you have detected, that match certain, that correspond with certain feature detections. Hopefully that was clear enough about why we just take ij and the offset, but really we might not even need ij because we're essentially moving this AB matrix all over, and there are certain values for each of the elements in this matrix, right? So don't forget that. And we're moving this all over the image. So we don't even care about where we start with because it's going to go all over the image anyway. And that's what this slide is saying, that really we don't even care about ij. We can drop the ij and we can essentially move this weight matrix all over the image and multiply it by the corresponding image. So X is this input image or input representation, if you want to take it somewhere in the middle of the network where you're not starting with the input, but you're moving on from a hidden layer, but you're still convolving. So input image or representation. And you're moving this, now I'm going to call this a filter or a kernel over this image. And the reason this is a cross correlation and not a convolution, and this I didn't know this, so this was very interesting to learn, is because convolutions are actually negative. Okay, maybe it doesn't spend time on this in the slides, but the idea was convolution goes for f of minus x and g of x, something like that. So in this case, you would have to go for f of minus a, b, minus a minus b, and g of a, b. And the problem is as a and b increase, or actually not even this, I shouldn't confuse you. The bottom line being convolutions make one function move backwards as the other function moves forwards, something like that, relatively. And the problem with this movement backwards is when you're considering matrices, what happens is you want to index, when your computer, like in computational memory, the caching caches the next values because it assumes that this is incrementing, this is moving next. And it it caches the contents of the memory that is indexed by the next location, to be extremely specific. But if you're actually implementing mathematical versions of convolutions, it actually calls the element in memory that precedes the current element. And that is the problem because that is not cached. So that causes thrashing, or you have to go back to your main memory, pull it into cache, and then call it from cache. But anyway, that for computational reasons, that is slower than just doing cross correlation, which moves forward, as you can see. And so convolutions are actually implemented as cross correlations. Hopefully that gave you an explanation that you can build upon if you like, but you don't need to know this unless you're going to do some theoretical convolutional neural networks work, which should be it. There's a lot of that going on these days. Anyway, so far we've gotten into the math. We've understood what the idea of locality is, which is we've understood the idea of translation invariance. We understood the idea of locality, which is just saying we shouldn't be going very far from this patch. If there is a face here, then this patch is all I care about. I don't care about what's here, nor what here, nor what's here. So I can just keep the weights outside this 0 because I don't care about this. And that's why it's motivating why your weight matrix can be smaller and not care about the other elements outside of that. I will pause here because there are two ideas we've gone through. There is a lot of math that we stepped through, and this displacement, this idea of discarding like the locations and 4D matrices might be a bit hard for some of you to digest. So ask me questions about it. Okay, if not, can someone step up and summarize what we've talked about so far? You can directly unmute yourself. I thought I heard someone, maybe not. Okay. Okay, I'm just going to summarize it again. We spoke about two ideas, translation invariance and locality, among other things like compositionality that I'm not getting into right now. But the idea is we want to detect where in an image a certain feature is present. We want to build a set of features in order to detect an object. In order to detect these things, we basically multiply a filter with an image, or we slide a filter over an image if you prefer that, or we convolve a filter with an image if you want to be mathematically precise. All of these imply the same mathematical operation, the convolution. The convolution is implemented as a cross correlation for computational reasons, and that's about it. These mathematical properties allow us to say that we just care about this particular section, drop the weights outside that section to 0 when you're studying it. And when you move across it, section by section, you consider patches of the image in order to create what you are then going to call feature maps. Again, we'll get into all of this terminology, but we started with some very simple idea that a face is composed of different parts. We want to detect these parts. Cool. This is just a visual depiction of what a convolution looks like. So when you slide this, when you convolve two functions f and g at different locations, and you should go back and spend some time on the slide because I'm not going to. It's just showing you when you're convolving the blue function with the red, as you slide the blue over the red, the value of your convolution goes higher and higher as they overlap more and more. So again, the overlap indicates the similarities in the functions. So the value of the convolution increases, overlap increases, and the value of the convolution decreases as overlap goes to 0. That's what this operation is essentially doing. And convolution of f star g and g star f is shown here. Not necessarily it's symmetric. Cool. Oh, sorry. Convolution is symmetric cross correlation. It's not my bad. What's that? I guess I shouldn't spend time on that. I'm not sure about that. If I need to think about it. Cool. So we spoke about one-dimensional stuff. We spoke about this in one dimension. We said there is an input image, there is a certain kernel or a filter or just a set of weights that you convolve this with. And because of this convolution, you produce a certain output. Well, how do you produce this output? This is how you produce this output. You can now see how you're convolving your image with your filter. So to be precise, the light blue is the image, the dark blue is the filter, and the green is the output you produce by placing this filter on this image. Right now, you're just summing them all up. So the equations just show you that you're multiplying the matrices together and you're summing up the output. There are different ways of doing this. For example, you can take, again, we'll get to this, but there is this idea of, well, can we do better than just summing them all up? Yeah, well, you can play around with that. There is this idea of taking averages. You can take maximum. You can, again, like I said, different ways of pooling the outputs produced by these convolutions. Going deeper into this idea, this is how you mathematically write it. You essentially want to convolve your image X with certain weights W and add a certain bias. The dimensionality, I'm not going to go into, you need to sit down and read this. It's no big deal. It's just saying kernel height times kernel width, layer height, image height times image width. So essentially, it's like a dimensionality analysis, which ties down what kinds of output, what is the dimension of the output you're going to get by convolving these two items. So let's get into some examples of what kinds of filters people have designed in order to detect certain features of the image or in order to obtain certain outputs by convolving images and weight matrices. And what's going on here is essentially this sort of feature. This sort of feature is used for edge detection. Why is this used for edge detection? Well, you can think about it as it weights the central element by a lot and weights the rest by almost nothing. And so it says if there is a certain edge, then these elements will have very different values from what my central element is. And so that will detect the edge that I have. So these filters mean something, and they are designed by someone to analyze certain features that are present in an image. In this case, those features are edges. And some smart people spend a lot of time doing this to design different kinds of filters. And so you want to add all of the features detected by these filters together in order to detect different parts of an image or different features present in an image. Similar idea, there is this idea of sharpening an image where you sort of discard the boundaries and you keep the central part. Similar idea of blurring where you sort of weight elements around the central part roughly the same as the central part, and you're like, oh, I'm taking combinations of all of these things and then summing them up. And it's just a kind of example of how you would apply this to a real image and what it might look like. So far we have studied, yeah, this was the slide I was looking for when I was talking about the difference between cross correlation and convolution. Should be due to symmetry. what I said was in convolution, you take f of minus a and minus b, and in correlation, you take f of a and b. And due to this minus a and minus b, as you change the values, you go into problems because your cache has not stored the next value that you need. So you need to go back to your main memory and pull that value. And you have to keep doing that. So when you do that billions of times, that is a big problem. um, I don't think I have anything more to say about that. The same idea extends to different modalities. When you talk about images, you have a certain height and a width to this image. When you talk about, this is just like I'm drawing a landscape now. When you talk about videos, videos are series of images. And so, and you might have heard of this, and this ties in with your idea of 24 frame per second, 30 frame per second. What is this? This is just showing you 30 different images in a single second, which makes it look like it is a video to you. Why do those videos from old days look like they're flickering? Well, because there are not enough images or enough frames per second in those videos. I think that's the right explanation. So yeah, I shouldn't have moved that. So if images are height, or we use this notation, right? We said images were number of pixels in the height times number of pixels in the width. Then videos now have this number of images in the entire sequence. So it basically tying into this idea of it going from 2-dimensional to 3-dimensional, or given that text is a single dimensional, like a sequence of words in a sentence, you have different sorts of dimensionalities that you have to account for, but the correlation operation remains the same, where you add certain offsets and slide that over the entire sequence. Similar for medical images, you want to think about this as 3D volumes, because it might be your heart scan, where you have a certain volume and your heart. I don't know if this is medically accurate, but I would imagine like a 3D volume is what you are analyzing. I know that a bunch of cancer detection challenges have involved 3D volumes, or maybe it's X-ray detection, X-ray analysis, chest X-ray. Anyway, you now know that there are different modalities and how we deal with those. So let's get into this idea of padding and stride. So when people are analyzing images, and again at this point, you have to now start thinking about what is new that I can do when I'm studying these images. And so people started thinking about what are we doing that can be changed. And they came up with these ideas where they said, okay, if let's go back one slide so I have some place to sketch, or maybe I should just, maybe I should just share screen here. Okay. This is visible. Yes, it is. Cool. They said we have two matrices. We are basically doing matrix multiplication, and I'm not even considering dimensionality here. So this is an image matrix, poorly drawn, but bear with me. And this is a weight matrix that I want to slide over this image matrix. And so what are the different things we can do that correspond to how we look at images? And sometimes when you have a lot of things going on in an image, and now I'm just like spitballing here because I'm trying to think of how we look at images and then trying to make the network do that. And we scan over an image and we miss out certain things and we look at certain other parts. And so some parts are interesting for us, other parts are not as interesting. And some features might be blown up, some features might be shrunk down. So again, in order to account for all of this, they came up with different kinds of ideas, which yeah. So they came up initially. The first idea was, okay, let's slide this over the image. Then they came up with this idea that, okay, well, if I'm sliding this, then at some point, every element, so at some point, this is here, right? And this is the central element, and these are the uh, boundaries of this element. But what about when I want to consider this as the central element? What if my face was here? And I shouldn't draw it outside the image. I should. What if my face was here? Well, then in that case, I need this filter to be exactly at the center or on top of this face. But it can't be, because like, what do I multiply? If my filter is outside here, what do I multiply this by? And that led to this idea of, okay, we should pad our images with something so the filter can move across the entire image. The second idea I was trying to go for is stride, where I want to say that, okay, maybe it's not important to slide this pixel by pixel, but maybe you can slide it by bunches of pixels. So if I start here, I want to then jump directly to here, because I don't think there is anything in the middle that might be as interesting, and that is called a stride. And again, like, I don't think if you have questions, ask me about it and make me explain this better to you. But as of now, I don't think there's a better way to explain it other than, like, if there are things in the boundary, you want to detect them. That leads to this idea of padding, because you want to treat each pixel equally. And then there is this concept of stride, because everything in an image might not be as important. You might want to look at it at a more granular, at a less granular level. Instead of sliding pixel by pixel, you want to slide by groups of pixels. Which might also tie in with analyzing high resolution versus low resolution images, because low resolution images might not need you to, yeah, that's what I want to say. And let's go back to the slides and wrap this up. Mm. So it's just a visual description of how padding works, where we've now padded this blue image matrix with a certain dotted background, well, dotted padding. Padding works in different ways. So you might want to just pad it with zeros. That is the simple way of thinking about padding, that, there is nothing outside this image, so we really don't care. But then there are new ways of padding that people came up with. They're like, well, you might want to pad it with some values. You might want to reflect the image in case there is some features you're detecting. And again, that's how innovation worked. And the way people came up with 1D convolutions, 2D convolutions, 3D convolutions, part of it was like, if you have to analyze videos, then you might want to consider, like, there is a certain object moving across different frames. So you might not just want to consider a single frame, like a kernel has to move in time. So across a bunch of frames, that's what in time referred to there. If you discretize your frames, then you multiply our kernel in a 3-dimensional space instead of over a 2-dimensional matrix. Fairly intuitive. This is just a dimensionality analysis of how padding works, and accordingly how the filter works. Not going to spend much time on that. Stride, again, what we discussed was, sometimes you want to look at things at a less granular level, and that's what stride helps you do. You don't need to look at it at a per pixel level. I guess the motivation for stride is computation, because again, looking at it at a per pixel level involves more multiplications than looking at it as at a less granular level. Nothing super crazy going on here. Nice depiction of how stride works. So now we're having a stride of 2, so just jumping um, across 2 pixels at a time instead of just 1. Hopefully that's straightforward enough. And the dimensionality analysis for when you have stride, what is your output? So Jay mentioned strides help us focus on a subpart of an image subsequence in a simple way. Seems straightforward. Again, the reason for this dimensionality analysis, like what happens when you're working with these, CNNs is, and I faced this myself a lot of times. I was like, what is going on? What if this is the layer and these are the settings for the layer? What should the input dimensions for the next layer be? And that's super confusing. So it's just annoying to have to sit down and calculate that. Modern deep learning frameworks do that much in a much simplified manner, but it's always important to know that if this is my stride, then I'm jumping 2 pixels at a time. That means my filter will have only 2 sorts of feature maps on this layer, and I have to combine those, and therefore this will be the dimensionality of the output. And so practically speaking, those are the things that are really important when you're building these convolutional neural networks. And therefore the emphasis on, if this is the stride, here is how you calculate the output shape. If this is the kernel size, this is how you calculate the output shape. Another thing I should mention is, like, I think in olden days we used to have really big kernels for images and like a very few number of kernels for images. And in modern times, you will see filters or kernels with 3x3 or 5x5 shapes. Even for like really high definition images which have a lot of pixels. And the reason for that is sort of, firstly, I think it's computationally more efficient, multiplying smaller matrices. um, there is a challenge that you're multiplying it more often, but that's where stride comes in. But the bottom line is, people realize that maybe smaller filters help you detect features better than these large filters seem to do. And so you have more numbers of filters but less size of filters compared to how it used to be. I hope that provides some sort of ideas for you when you try to implement these things. And the last part of this chapter that we're going to get into, or the second last part, is about input and output channels. And we spoke about this in some sense in the first slide itself, but to get back to the idea, if you have a certain image like this, which is an image of a Playboy model, because engineers or who are designed the field, my guess would be they are largely men. And this is the result when you put a lot of men in a room and try to do image processing. But I'm part of the problem. So anyway, this image can be decomposed into 3 channels, which is red, green, and blue. And this is what I meant when I said this image, that there are certain channels for an RGB image. The way we handle channels is by treating each channel independently and then combining or concatenating all of them, and then passing kernel over the channel over the concatenated group of channels. The reason we don't average this out is there are certain features that, even if you look at this, might be more visible to you. And for instance, there are, like, green seems to me more clear than red. I don't know why. I don't know if that's a problem with my eyes, but seems to me that way. Which means, like, even if you, um, I guess clear is not the right term, but again, let suffice it to say that there are certain features visible in certain channels that you have some information about, that if you just try to average it out, you're going to lose that information. And as why you're going to lose it, you should try it out and take this image. It's a fairly popular image, probably already present in the deep learning library you have in some dummy data set. Try to average it out and plot the image, and you'll see what I mean. And I did that, but I forgot to take a screenshot, so I don't have that. But anyway, That's the point. You have multiple input channels, so you have kernels for each channel, and then sum up the results over channels using whatever scheme. Again, simple way is averaging, but there can be better ways of going about it. So people came up with those. So what you're saying is the same convolution operator applied across channels, and then you simply sum up these channels from whatever channel 0 to number of channels. Super straightforward. No, nothing changes. Your dimensionality is now channel times the height times the width. Kernel is now channel times the kernel height times the kernel width, and your output is accordingly whatever height and width you get out of it. Cool. The same point, trying to be driven home. You can have multiple 3D kernels, each one generating an output channel, and you can find out innovative ways of combining those output channels. So instead of your y, oops, where was I? Yeah, instead of your y being just height times width, now you have a channel times height times width. So the bottom line is, in the end, you have to come up with predictions, intermediate representations. You can come up with your own intuitions to build these representations and think about how you look at images and how you want your network to look at images. And that's largely how, and we're going to get into ResNets in the next lecture. And so that's how these network architectures came about. People just sat and thought about how you look at images, how they think your brain processes images, and they were like, okay, this is the network architecture I'm going to come up with, and I think this architecture makes sense because our brain forgets some parts of images and focuses its attention on other parts of images, and it combines different channels in certain ways, and it processes things. And like all of these architectures, everyone has an explanation, but a lot of times the way they came up with it is just like just trying out different things without any motivation to do so. So why does mean pooling work better than average? Why does mean pooling work better than max pooling, or max pooling work better than mean pooling? Well, empirically, and that's the explanation people use for a lot of things in machine learning. And then when empirically was not enough, because when you publish a paper, people want you to have a theory for why it works. Then after you get the result, people sit down and build up a theory about this is why we think this works, and then other people come in and say, but if you use this theory, then here is this other thing we should do but we aren't doing, but that doesn't work so well. And they're like, well, that is an exception to our theory. And again, it goes on like that. And again, I also will probably do this at some point in my life. But the point is, it's not, everything is not as intuitive as you think it is. Sometimes people just try out different things because they can, and they get great results, and so they come up and tell everyone, hey, we have great results, but we don't know why it is. So we need to normalize this a bit more, like, okay, here are results, let's talk about why this might be the case, or if it's just by accident. But that's not how you publish papers, so that's just the harsh reality. Yeah, it's great that this is being recorded. I'm going to be too lazy to edit it out, so one day this will bite me. But it is nice that these days there is a lot of theoretical analysis going on as to why deep learning, or a lot of very simple things in deep learning, seem to work. And that's all I have to say about that. So there is progress. It's just like at some point, like if a student builds something, they're not always going to have the intuition for it, and that's okay. That's completely okay to do. So don't let that restrict you from experimenting with different kinds of architectures and things to do. And that is end of rant. Let's get back to the topic at hand. Also, I haven't had any questions so far, so feel free to pause, ask me questions. I am assuming that you're all fairly familiar with CNNs, which is why like a bunch of people just dropped off. And like I'll also try to close early in like 10 minutes. But I'll be around for 15-20 minutes after that, so you can always ask me questions. Do kernels allow us to be a bit more flexible with image size in our training data? That is an interesting question. I don't see any limitation to, or if you want to clarify that question, I don't see any limitation to image size and kernels. So only thing I would go back to is the point about earlier we used to use larger kernels, now we use smaller kernels and different kinds of kernels. Earlier they used to be hand designed. Again, like we go back to the HAR example. Like people sat and hand designed features and kernels, but now we're just like trying out different kinds of kernels, seeing if they give us features automatically. So your deep learning library comes with a bunch of kernels inbuilt into it. So you can just dump all of those on your, try out all of those on your data set. Sorry, you were saying something.
So to be more specific, like in your example, you had a 12 megapixel camera. Could you say use just like say an 11 megapixel or 10 megapixel picture as well in your training data, or does it all still strictly have to be 12 megapixels?
You could still just as well use 10 or 5 megapixels. So megapixels have to do with this image is converted into a higher definition matrix than a lower definition matrix, by which I mean like it has more pixels, has less pixels.
Okay, thank you.
But that has nothing to do with the kinds of kernels you can apply to it. You can still apply the same kernels. You can't apply a bigger kernel to a smaller image, if that's what you mean.
Yeah, that's what I mean. Thank you.
Yeah. So then you would have to pad the image to fit the size of the kernel, and then the padding would have to be determined. And if your padding is more than your data, then you're basically just learning on simulated data. So that's a problem. But yeah, if that was the question, then yes, smaller kernels allow you to work with larger images. But really, like kernels are so small and images are so big that this really doesn't matter with modern deep learning. Cool. Thank you for the question. Moving on to ending early. This we already spoke about. Each output channel may recognize a particular pattern. So we spoke about the feature maps. Each kernel is trying to detect a different kind of feature. Input channel kernels recognize and combines patterns in input. So as you add more layers, now you're going from image to features to combinations of features. So this ties into the idea of compositionality, that your first layer might not be learning a nose. It might just be learning your nostrils or like black dots near your face. And then as you go at higher and higher layers, they combine these smaller level features. So one feature might be your nose, one feature might be your eyes, one feature might be your mouth. And as you go higher in the network or deeper in the network, whatever you want to call it, you start combining these lower level features, and that brings us to this third idea that we discussed when we are talking about the face, which says compositionality. So you want your network to compose these lower level features into higher level objects. So yeah. Okay. Smola makes a point about this 1x1 convolutional layer, which we have actually studied before. And can you tell me like what are you doing if you're looking at a 1x1 convolution? I change the slide here, so hopefully I don't think it had the answer on it, but generally, like, can someone speak to like what is a 1x1 convolution?
We are basically transforming the image to something else. If 1x1 kernel is applied to a bigger image, I think.
Exactly. So you're looking at it pixel wise, so which is essentially a linear transformation. You're applying a weight matrix to each pixel of an image, which we have already discussed. We do that in a matrix form for a multi-layer perceptron. You multiply wx plus b. You are still multiplying wx plus b because you're not averaging it over any local set of data. You're just looking at 1x1. And so that's exactly what he says. This is as good as just applying a multi-layer perceptron to the image, equal to a dense layer with whatever times channel input and whatever weight that you're looking at. Again, like a transform, more than a convolution. Cool. And so it's not going to get into the details because we've spoken about all of this. And this is more about computation, which I feel is sort of distracting. But I will get to the pooling layer really quickly because I've spoken about this already. The way that the reason we use pooling is because at some point you want to reduce the size of your input, but in a meaningful way. And so I don't think I want to. This is fine. Yeah, I want to show you this image, this video about like what pooling is doing. The way you reduce, so pooling is this idea of reducing the light blue image to the to the light green image in a meaningful way. And the key is in a meaningful way. And so if you place a kernel over this, like we discussed, you can sum it, you can average it, you can take the maximum, you can take the minimum. You can apply any operation to it, and there are different reasons that people tried out different operations. Max pooling worked better empirically, so people started using max pooling really like a lot. um, I don't think there's anything super important to say about that. um, I think Smola gives you an example of edge detection, which again, not super important. um, So I'm not going to spend much time on that. I would rather give you the time back and spend time on questions after the lecture if people have any about projects or otherwise. So pooling layers have similar padding and stride as convolution layers. There are no learnable parameters. Again, it's an operation you're applying. So your choice of operation has already determined your pooling layer. Okay, this is important. Your average does not come with any parameters. Your average is just a sum of values upon number of values. There is no learnable parameter in the average pooling layer. In the max pooling layer, again, no parameter that is determining this pooling. It's only like when you choose to apply pooling, right? So number of output channels is the same as the number of input channels. So for pooling layers, you don't have to care about the inputs and outputs because they don't change. To be specific, the dimensionality. I mean, dimensionality does change because you take the average, but hopefully you get the sense that channels do not change. I take pooling across, pooling across each channel. Yeah, okay. Intuitively, max pooling works well. Jay posted on chat. Intuitively, max pooling works well because if you're giving more weightage to the features that are relevant instead of average over all the features or other pooling operations, it makes sense that you want to detect the feature that is important. This is fair. But, and I think Smola discussed this in his video also, that people did this, it worked well, and then they came for the explanation. Yeah. So max pooling, the explanation for this is the strongest pattern signal in a window is what you want to detect. So average pooling is just you're taking the average signal strength in the window. Signal again refers to the object you might be wanting to detect. And again, LeanIt, there's already a discussion of this that has happened, so I'm not going to get into this. I would rather pause here. We have about half an hour left. So I can pause this here, take questions, or discuss other things that people want to get through. Because next week onwards, we'll start having project presentations, and we will also have a midterm in 2 weeks' time. Or you can call it a final because we have just one exam. It is completely optional. It is designed, though I would highly recommend it because it simulates the experience of an exam that you're going to have at the same level as that of like grad school. We've kept the questions solvable in the sense like you're not going to have to struggle to solve them, but you will have to spend time. It's not straightforward. They are based on concepts in your first few weeks lectures. Again, I can do this after I pause the recording first. I can take some questions and then I can get into logistics. So to start with, are there questions about the lecture?
Swapnil, I think we should also mention a bit more about like why one cross one convolution is probably more useful, and like maybe it has like smaller amount of parameters and it obtain some similar results, right? Basically increasing the channel with sort of like basically maybe but yeah.
I couldn't hear you very clearly, but if you want to,
Like basically what I am saying is, so in using one cross one convolution, you are basically getting sort of the same transformation in a way, and like we see your parameters are not much, like we see. So it is also computationally much more efficient, like we see, compared to other techniques which would like give you, let's say, using this particular multi-layer perceptron, one hidden size also, like hidden layer basically. So instead of that hidden layer, if you apply one cross one convolution, that would be much more parameter efficient, like we see, like it has lesser parameters.
Are you saying weight sharing? Is that what you're getting at?
uh, yeah, like basically the weights are very low, like because if it's a one cross one convolution, let's say there are like some k kernels, like,
You're,
right?
it's like you're applying a multi-layer perceptron with the
Yep.
same weights. That's what you're getting at, right?
Yeah, but I think they are like, but the weight matrix is like smaller than the perceptron, like, or like a hidden dense layer basically transformation. What I mean.
I see. I think I
Just
got your point, but
yeah,
I
because in
I
dense layer
don't.
it would be, sorry, go on.
Mhm.
Like in dense layer it would be like basically a very higher matrix sort of, but in using this one cross one convolution you can get the same result with very smaller parameters, like basically, so your network parameters are not much exploded in a way.
All right. Thanks. That is helpful to know. So I I think the point being driven home, and you already heard all of it, but the point being driven home was the efficiency of one cross one convolutions versus a densely connected multi-layer perceptron, where due to there's a smaller number of weights involved in the one cross one convolution um, compared to the multi-layer perceptron. So uh, anyway, I will, if there are no questions, then I will.
So does that make learning better or worse? Because I don't think then parameter sharing, which was the concept of convolutional networks, is introduced in one cross one convolutions.
So I think the learning better and learning worse is like we're talking about two separate things. Learning better and learning worse depends on what is the nature of the data set that you're operating on and if CNNs are suited for it. What the point of being driven home was about computational efficiency. So learning will be faster. We don't know if it will be better or not. Is that,
That
yeah?
makes sense. Yeah, because like all the most we do not know what the hell we are learning in actual models, right? Like
Fair.
whatever be the filters they produce, the model produces in itself. For every
Fair.
different model, it will be different. So ultimately, the main decision making task is going in the dense layer itself, right?
In a sense.
So whatever be the filter, the model suits it best to the type of image. Maybe
I
that's the point.
agree with what you're saying, but that, are you getting at like are MLPs or CNNs better for images in general?
Yeah, because like in a sense, it is reducing the dimensionality of the image versus and also increasing the like if we are increasing the number of filters, then the chances of getting a new type of information increases. So, but the whole image compared to the whole size of the image which we feed in, that would be much more like complicated or complex to process in a computer. Computation efficiency. There we go.
I did not completely follow. It was kind of a long question, but maybe you could summarize it for me.
It wasn't a question, I guess. It was my
More of a comment.
yeah.
Got it. Yeah, in that case, I sort of said I would say that again, it's very use case dependent because for object detection and stuff, sure, CNNs work better. But there are other use cases where people just used encoder and decoder networks to work with images and compression and stuff like that. I don't think I don't know if there is a convolutional VAE. I think VAE is just use multi-layer perceptron. So
There is a convolutional VA like for speech recognition that I did from a YouTube channel. So if you're asking,
gotcha. My point was like VAEs grew popular with the use of MLPs, but they work on images. So it's not like domain. It's not like anything to do with images will only involve CNNs. Like there are um, graph nets that are essentially like graph convolution operations are like not exactly convolutions. It's like summing up your neighbors, that sort of thing. So it's like message passing on graphs. But they are fully connected. They're just MLPs, fully connected layer, and they work reasonably well for a lot of image related tasks. So again, I'm making very vague and general statements, but maybe the point I'm trying to get at is like some networks are great for some kinds of data, but exceptions exist. Like it's not all the time that you're going to get the best results with the same architecture or the same class of architectures. Okay, I should at least.
I think like one more point to add sort of for like why CNNs are much more popular for image related data is like it helps you focus on like sub parts of the images like basically intuitively, and then you can go through it and like kind of get sort of relevant features that are more important. So like you are basically repetitively going through different sections of images, like basically different subparts of images. So that is why like they are more powerful as well. Like,
yeah, we are also at the same time discarding noises or anything which
yeah,
is not relevant to the
yeah.
model. Yeah.
Yeah, but that is not limited. Like CNNs are also applied to other tasks as well, like language related things. So yeah, but like they are more useful, like prominent in image related applications.
Fair point. In fact, there was a certain application that converted text into images of text and then applied CNNs on that image in order to obtain a better sort of output or better perform better on the task at hand than they would have directly achieved. So very curious applications like converting an image to text and then working on text just because CNNs are so good at dealing with images. So that's seems interesting. But anyway, I'm going to pause recording here.